Here in the quiet darkness, a single point of light persists, a pale blue dot suspended in a sunbeam. Upon its surface, a film of water, a breath of air, a shimmering, fragile veil of light. Of all the worlds we have glimpsed across the staggering expanses of space and time, this is the only one we know for certain harbors the phenomenon we call life. Whether that life can yet be deemed intelligent, given its tumultuous adolescence, is a question for philosophers and historians. Yet the impulse that drives us to peer into the cosmic ocean, to search for another flicker of consciousness in the void, is perhaps the most profound expression of that very intelligence, or at least its most desperate hope. We are lonely. We yearn for company, and so, with telescopes and equations, with relentless curiosity, we scan the heavens, seeking a reflection of ourselves, or perhaps something wondrously other. For millennia, the planets were mere wanderers against the fixed tapestry of stars, mythic gods, and celestial omens. Then they became worlds. Our solar system, once the entirety of our conceivable universe, revealed its stark diversity: the searing inferno of Mercury, the shrouded greenhouse of Venus, the rusted deserts of Mars, the majestic gas giants with their dancing moons. For a long, quiet century after, we wondered if this barren archipelago was all there was. Were the other stars merely lamps in the night, or did they too host families of worlds? The answer began to trickle in, then flood. A new age of discovery dawned, not of continents but of cosmography. We found them, worlds beyond our sun. Exoplanet. The tally now stands in the thousands, a census of alien orbs, each a revolution in our understanding. They are a menagerie of the improbable, hot Jupiters baking close to their stars, diamond worlds, planets with two suns, rogue worlds cast adrift into the interstellar deep. Amid this cosmic chaos, we search for order, for familiarity. We look for the gentle curve of a habitable zone, the spectral hint of water, the atmospheric fingerprint of an Earth in waiting. And in this search, we have been humbled to discover that our Earth, for all its beauty and complexity, may not be the pinnacle of planetary engineering. It may, in the grand galactic scheme, be merely adequate. The National Aeronautics and Space Administration, synthesizing data from Kepler, TESS, and other planet-hunting missions, compiled a quiet manifesto of cosmic real estate. Not just a list of Earth analogs, but a catalog of worlds that are, by certain meticulous criteria, 24 planets where the conditions for life, and perhaps for a stable, enduring civilization, might be more favorable than on our own turbulent sphere. This is not a critique of our home, but an expansion of possibility. It is the realization that the universe, in its boundless creativity, may have authored versions of the habitable world more temperate, more enduring, more spacious than our own. Let us embark on a journey to a few of these distant superior Earths, understanding that we see them only through the most delicate and indirect of methods: the faint dimming of a star's light, the subtle wobble of a stellar dance, the ghostly signature in a spectrum. They are hypotheses made of data, dreams rendered in mathematics. Our first destination lies in the constellation of Cygnus, the Swan, a region strewn with the ghosts of dead stars, and the nurseries of new ones. Here we find the candidate known as KOI 575, a 01, a string of numbers and letters that belies its significance. To comprehend its promise, we must first look to its sun. Our star, the Sun, a G-type yellow dwarf, has been a faithful engine of life for 4.5 billion years. It is steady, reliable, but in the grand stellar taxonomy, it is not a long-lived patron. Its hydrogen fuel will sustain it for a total of roughly 10 billion years. We are comfortably in its middle age, with perhaps 7 or 8 billion years of stable luminosity remaining before its final swelling transformation. This is a generous span, far exceeding the lifetime of any species this planet has yet borne. But for a universe that operates on scales of tens of billions of years, for the potential of life to evolve into forms of profound stability and wisdom, our sun's tenure is but a bright, fleeting day. KY 5715L1 orbits a different class of star altogether, a K-type orange dwarf. Slightly smaller, cooler, and dimmer than our sun, these stars burn their fuel with a thriftier, more measured pace. Their lifetimes are extraordinary, stretching from 45 to 70 billion years. They are the marathon runners of the main sequence, offering a stability so profound it defies human imagination. A civilization born under an orange dwarf could witness the slow drift of galaxies, the steady transformation of its own planetary system over epochs that make our entire geological record seem like a brief afternoon. The star itself becomes a near-permanent fixture in the heavens, a guarantor of environmental constancy. For life, time is the ultimate laboratory. More time allows for greater experimentation, for recovery from catastrophes, for the slow, cumulative accretion of complexity. An orange dwarf offers not just a place to live, but a place to endure. Ideally, we would seek a planet around such a star that is already ancient, perhaps 7 billion years old, a world that has had ample time to cook the primordial soup, to pass through its volatile youth, to perhaps have given rise to intelligence that has long since learned to live in equilibrium. KOI 571501 is estimated to be about 5.5 billion years old, a little older than our own Earth. It is not yet the elder statesman we might envision, but it is mature. Its age suggests a world that has settled into its geological rhythms, its crust stabilized, its magnetic field possibly still dynamo-driven by a liquid core. It resides comfortably within its star's habitable zone, the region where temperatures allow liquid water to exist on the surface. A year on this world is a swift 190 Earth days, a consequence of its closer orbit to its dimmer star. To grow up on such a world would be to experience the passage of seasons at a different rhythm, to mark the years with a quicker cadence. It is a larger world than ours, a so-called super-Earth, with a radius nearly twice that of our home planet. This has profound implications. Its stronger gravitational pull would sculpt a different world. The atmosphere, if it possesses one, would be denser, thicker, more tightly held. This dense atmosphere acts as a global insulator, distributing heat more efficiently from the sunlit side to the night side, mitigating temperature extremes. It also provides a formidable shield against cosmic rays and ultraviolet radiation, and allows for a greater atmospheric pressure at the surface. The average temperature is estimated at a cool 52 degrees Fahrenheit, slightly chillier than Earth's 57. But due to the atmospheric density and greenhouse effects, we can only infer the perceived climate. The actual conditions in the valleys and on the shores could be remarkably temperate, even balmy. The skies, filtered through a thicker air mass, might blaze with more intense colors at dawn and dusk, the blue of the daytime sky perhaps deeper, more profound. But here we encounter the first and most persistent reality of our search. This promising world, this potential paradise, lies approximately 3,000 light-years from Earth, a distance that translates to about 18 quadrillion miles, a number so vast it loses meaning, becoming only a monument to our isolation. To contemplate a journey, there is to confront the fundamental limits of flesh and steel of even our most ambitious. It is a world seen as it was 3,000 years ago, when the Bronze Age empires were crumbling on Earth. Any signal we might send would not arrive for 3 millennia, and a reply would take another. It exists, for now, in the realm of celestial possibility, a template for what might be, rather than a destination. Yet, its very discovery reshapes our thinking. It tells us that the ingredients for a stable, long-lived biosphere are not unique, but are likely sprinkled throughout the galactic disk, orbiting the faint orange embers that are among the most common stars in the Milky Way. Let us turn our attention to another candidate, KOI 13001. The data here paints a picture of a world that scientists describe with a hint of awe, not just Earth-like, but potentially more pleasant. Its estimated average surface temperature is 67 degrees Fahrenheit, about 10 degrees warmer than Earth's global average. This is not a trivial difference. Within the habitable zone, there is a thermal sweet spot. A slightly warmer planet, all else being equal, tends to be more conducive to a vigorous hydrological cycle, to more widespread liquid water, and to a greater diversity of biochemical reactions. Ice is confined to the poles or high altitudes, and the temperate belts where complex life might flourish expand. Some climatological models suggest that for a planet of Earth's size and composition, an average temperature several degrees higher than our own might actually optimize biological productivity. This world is another super-Earth, about 1.5 times the size of our planet. The data suggests the presence of an atmosphere, its composition still a mystery, but the hope, based on modeling and its position, is for something akin to our own nitrogen-oxygen mix, perhaps with a higher proportion of water vapor. There is strong indication of surface water. Scientists speculate an ocean covering up to 60% of the planet. This balance is intriguing. Earth is a water world, with oceans dominating 71% of its surface. A slightly lower percentage, a more equitable distribution between land and sea, could be advantageous. More land mass means more territory for continental ecosystems to develop, greater mineral resources exposed, and potentially more room for the emergence and spread of land-based life. It suggests a world of vast archipelagos, of great continents not drowned by shallow epicontinental seas, a planet where the coastline is a dominant but not overwhelming feature. The resemblance to Earth is so compelling that statistical analyses have given an 84% probability that this world hosts some form of life. This is not a guarantee, but a compelling odds ratio in the cosmic casino. It speaks of a convergence of favorable factors: the right temperature, the likely presence of water, a stable orbit, a mature star. The life, if it exists, would have evolved under a stronger gravitational pull. Imagine the evolutionary pressures. Flying, if it develops, would require more power, more robust wings. Large towering forms like our trees or dinosaurs might be structurally challenged. Life might favor a lower, stockier, more muscular profile. Animals might be built like tanks, with thick bones and powerful limbs, to move under the greater weight. Could intelligence arise in such a world? Perhaps it might be an intelligence born of deliberate, powerful movement, of a different relationship with the very ground it walks upon. They would look upon their dense, warm, well-watered world as the only conceivable home, its gravity not a burden, but the essential force that shapes their reality. But again, distance intercedes. We see this promising world as a flicker in the data, a single pixel of inference. To know its truths, to see its continents and oceans, to detect the chemical signatures of its biosphere, will require telescopes of a power we have only just begun to conceive. Our search leads us next to a landmark discovery, Kepler 186f. Heralded as Earth's cousin, it was among the first near-Earth-sized planets found solidly within the habitable zone of another star. It orbits an M-type red dwarf, the most common type of star in the galaxy. These are frugal, diminutive stars, far dimmer and cooler than our Sun, with lifespans that stretch into the trillions of years, virtual immortality on a cosmic scale. Their faintness means their habitable zones are close in, snug orbits. Kepler 186f hugs its star, completing a year in just over 130 days. This proximity comes with consequences. The planet is likely tidally locked, with one hemisphere in perpetual daylight and the other in eternal night, or it may possess a very slow rotation. This could create extreme weather patterns, with fierce winds transporting heat from the day side to the night side. But the view from the surface, at the terminator line between light and dark, would be unforgettable. The sun in the sky would be a deep, furious red, 3 times larger in apparent size than our sun, but pouring forth only a fraction of the light. The sky itself, if the atmosphere scatters light at all, would be bathed in perpetual sunset hues, crimsons, oranges, and violets, a world of eternal twilight. The planet's size is nearly identical to Earth's, which is both comforting and, from a certain perspective, a missed opportunity for the super advantage. A larger planet, as we have considered, holds its atmosphere more securely. Yet, Earth's size has proven more than sufficient. What Kepler 186f may boast is stability. Its axial tilt appears to be modest, similar to Earth's. This is a critical detail often overlooked. A planet's tilt, its obliquity, is the governor of seasons. Earth's stable tilt of about 23.5 degrees, maintained by the gravitational influence of our large moon, gives us the predictable rhythm of spring, summer, autumn, and winter. This rhythmic change drives migration, hibernation, agriculture. It is woven into the fabric of our biology and culture. Now consider Mars. It too lies within the Sun's extended habitable zone, but Mars lacks a large stabilizing moon. Its tilt chaotically wobbles over millions of years, from nearly 0 to over 60 degrees. This climatic chaos can cause the poles to melt and the equator to freeze, driving any surface water or nascent life to extinction. It is a primary reason Mars is a desert today. Kepler 186f's stable tilt suggests it too could have regular seasons, a stable climate over geological time, a foundation upon which life could build complexity. This planet, a world of red sunsets and earthly proportions, lies some 490 light-years away, a mere stone's throw in galactic terms, yet still an unbridgeable gulf with current technology. It is a symbol, a proof of concept, that planets of our size exist in the temperate zones of other stars. Before Kepler 186f claimed attention, the titles of most Earth-like belonged to a pair of worlds in the constellation Lyra, Kepler 62e and Kepler 62f. Orbiting the same red dwarf star, they present a fascinating study in sibling worlds. Kepler 62e is about 1.5 times Earth's size, while 62f is slightly smaller. Their years are brief, just 122 and 267 days respectively. The most captivating hypothesis about these worlds is that they may be water worlds. Theoretical models and their low densities suggest they could be covered in global deep oceans, perhaps hundreds of kilometers deep. If any land exists, it would be the peaks of submerged mountain ranges, isolated islands in a planet-spanning sea. Such a world fires the imagination. It is a planetary-scale aquarium. The pressures at depth would be crushing, creating layers of exotic ices. But in the sunlit upper layers, a rich aquatic biosphere could thrive. Evolution in an endless ocean with no barriers would follow a unique course. Intelligence might emerge in a marine species, building cities of coral and communicating with complex sonar songs. The concept of land would be mythological. For humanity, a water world presents profound challenges for colonization, but also incredible resources. It is a reminder that habitability does not mean human habitability without monumental effort. These worlds, lying over 1,200 light-years distant, embody the diversity of the habitable condition. Life, if it exists there, would be truly alien, shaped by a universe of blue. These are but a few specimens from a growing catalog of superiority. The very notion of a better Earth forces us to define what we value: longevity, stability, resource abundance, climatic mildness. It compels us to look beyond our parochial experience and admit that our world, for all its splendor, is not the final word in planetary design. It has its flaws, its tectonic violence, its climatic oscillations, the relatively brief lifetime of its sun. The discovery of these 24 worlds is a quiet revolution. It says that the universe is not merely capable of making copies of Earth, but of iterating, of improving upon the template. Yet, this revelation is tinged with a profound irony. As our catalog of potential paradises expands, so too does our awareness of the distances that separate us. We are map makers of a continent we cannot reach, cartographers of the very telescopes that reveal these worlds to us also underscore our confinement. For now, they are subjects for study, not destinations. Their promise, however, fuels the next great leap in our astronomical endeavor, the move from detection to characterization. We must learn to read the light that passes through their atmospheres, to decode the molecular signatures of oxygen, methane, water vapor, and perhaps even the techno-signatures of civilizations that beat us to the starting line by billions of years. The torch for this next phase of exploration has been passed to a new generation of observatories, most notably the James Webb Space Telescope. Its name honors a pivotal administrator of the National Aeronautics and Space Administration during the Apollo era, but its vision is fixed on epochs far more ancient. After 2 decades of design, construction, and nerve-wracking deployment, this technological marvel now orbits at the Lagrange point known as L2, 1 million miles sunward from Earth, its back forever turned to the Sun, Earth, and Moon, its gaze fixed on the deepest cosmos. The James Webb Space Telescope is not merely an improvement on its predecessor, the Hubble Space Telescope. It is a transformation in kind. Hubble showed us the universe in visible and ultraviolet light, the light our eyes see. Webb sees in the infrared. This is the key to unlocking the universe's deepest secrets. Infrared light has longer wavelength than visible light. It can pierce through vast clouds of cosmic dust that obscure stellar nurseries in the hearts of galaxies. Furthermore, due to the expansion of the universe, the light from the most distant, ancient objects is stretched, or redshifted, from visible wavelengths into the infrared. To see the first galaxies, one must have infrared eyes, and that is precisely what Webb provides. Its primary goal is audacious: to witness the cosmic dawn, the epoch when the first stars and galaxies ignited, ending the dark ages that followed the Big Bang. It seeks to understand the assembly of galaxies, the birth of stars, and the formation of planetary systems, but its power also revolutionizes our study of nearby exoplanets. For the first time, we have an instrument capable of taking detailed spectra of the atmospheres of Earth-sized worlds orbiting other stars. This is the difference between seeing a dot and reading its chemical biography. Consider one of Webb's early images, a seemingly chaotic tapestry of color and form, a stellar nursery. Here, in a region of space similar to where our own sun was born, we see jets of material screaming from the poles of infant protostars, fierce stellar tantrums as they gather mass. Glowing clouds of molecular hydrogen, the raw material of stars, are painted in crimson. Dark shadows streak across the nebulosity. These are protoplanetary disks, swirling frisbees of gas and dust, where planets are coalescing. What appears as beautiful chaos is, astronomers assure us, a relatively quiet and small nursery. Many of the young stars here are of solar mass or smaller. This image is not just a photograph, it is a birth announcement for future solar systems, a glimpse into our own origin story, 4.5 billion years removed. Webb's power to probe chemistry across cosmic time was stunningly demonstrated when it detected the spectral signature of complex hydrocarbon molecules, essentially smoke or soot, in a galaxy a staggering 12.3 billion light-years away. This galaxy, as we see it, existed just 1.5 billion years after the Big Bang. The discovery pushed back the record for such complex chemistry by 1 billion years, revealing that the universe became chemically enriched, creating the building blocks for future planets and life. With astonishing speed, it tells us that the ingredients for worlds like ours were being forged in the very first generations of stars and spread through their explosive deaths, seeding the cosmos with carbon before many of the galaxies we see today had even fully formed. In the realm of exoplanets, Webb has already begun to deliver on its promise. It confirmed its first new exoplanet, LHS 475b, a rocky world almost exactly Earth-size, a mere 41 light-years away. While its surface temperature is too high for habitability, the demonstration was flawless. Webb is now the only tool humanity possesses that can analyze the atmospheres of terrestrial exoplanets. It will seek the telltale signs of biogenic gases on worlds in habitable zones, looking for the atmospheric disequilibrium that shouts life. The research teams hope this precision will lead us to the first unambiguous evidence of a living world beyond our own, and perhaps identify targets for future, far-off mission. The telescope's infrared vision also unveils the violent and beautiful ends of stellar lives. It captured WR12-4, a massive Wolf-Rayet star in a frenzied pre-supernova state. These stars are rare, monstrously large, and shed their outer layers in furious winds, creating a gossamer nebula of ejected material around them. Webb's image shows the star blazing at the heart of a maelstrom of hot gas and dust, a cosmic chrysalis moments from the cataclysm of a supernova. In that ejected material are heavy elements: oxygen, carbon, iron that will one day be incorporated into new stars, new planets, perhaps new life. Webb shows us the cycle of death and rebirth in exquisite, terrifying detail. Perhaps one of Webb's most visually and conceptually arresting early discoveries is the object known as VHS 156b. This is a world that defies easy categorization. It is a brown dwarf. These are the cosmic in-betweeners, objects more massive than the largest planet, but too small to ignite sustained hydrogen fusion in their cores. They are failed stars. VHS 156b is nearly 20 times the mass of Jupiter. It emits a dim, ruddy glow from the residual heat of its formation and from limited deuterium fusion. It orbits not one, but two red dwarf stars, taking an astounding 17,000 years to complete a single orbit, a languid dance in a gravitational embrace. What makes this object extraordinary is what Webb's exquisite spectroscopy revealed about its atmosphere. For years, theorists had predicted that in the cool, turbulent atmospheres of brown dwarfs and giant exoplanets, conditions might allow for the formation of clouds, not of water, but of silicate minerals, essentially clouds of sand. VHS 156b provided the first unambiguous evidence. Its atmosphere is a dynamic, violent place, with temperatures reaching 1500 degrees Fahrenheit, and upwelling plumes of material carrying tiny grains of silicate vapor high into the sky, where they condense into minute sand-like particles less than a micron in size, forming patchy, swirling clouds. The atmosphere also contains water, methane, carbon monoxide, and carbon dioxide, a complex chemical brew being churned by supersonic winds. This is a world with a molten sandstorm for a sky, a place where the very concept of weather is alien and mineral. It demonstrates the incredible diversity of atmospheric phenomena the universe can concoct. Webb's power to challenge established theory was perhaps most starkly revealed with the detection of massive, mature galaxies in the very early universe. These galaxies, as observed when the universe was a mere 500 to 700 million years old, appear to be as massive as our Milky Way and are full of old, red stars. This presents a profound puzzle. According to our prevailing models of cosmic structure formation, there simply should not have been enough time for such vast amounts of matter to coalesce, form stars, and for those stars to age into redness. It is as if we discovered a fully grown adult in a photograph of a kindergarten class. This discovery does not necessarily break our cosmology, but it strongly suggests that the early universe was far more efficient at building galaxies than we thought, or that some fundamental process is missing from our simulation. Webb is forcing a rewrite of the first chapters of galactic history. Its deep field images, such as that of Pandora's cluster, showcase another of its capabilities. Pandora's cluster is not one, but three massive galaxy clusters in the process of merging. Their combined gravitational field is so immense that it warps the fabric of space-time around them, creating a natural cosmic lens. This gravitational lens magnifies and distorts the light from far more distant galaxies behind the cluster, stretching them into faint arcs of light. Webb's image of this region is the deepest, sharpest infrared view ever taken, revealing thousands of these background galaxies, some from the first billion years of the universe. It is a demonstration of using gravity itself as a telescope, and Webb is the perfect instrument to peer through these natural lenses. In the Tarantula Nebula, the largest stellar nursery in our galactic neighborhood, Webb's infrared eyes saw through the obscuring dust that Hubble could not penetrate, revealing tens of thousands of never-before-seen young stars. It captured protostars in the act of accreting mass and detailed the nebula's complex structure shaped by the fierce radiation of its most massive inhabitants. It has witnessed the birth of stars in distant galaxies, some with protoplanetary disks already in place, promising future planets. Each image is a dataset, a trove of information that will keep astronomers busy for decades, slowly unpacking the physics of creation. Among these discoveries are constant reminders of scale and mystery. Webb has studied a supermassive black hole, 9 billion times the mass of our Sun, a leviathan from the early universe whose very existence challenges models of how such objects could grow so large. It has detected a ring of gas and dust around a young star containing methylcation, a carbon molecule that is a crucial building block for more complex organic chemistry, the kind that leads to life. It has inferred the presence of silicate sandstorms on a distant exoplanet, 235 trillion miles away, and it has returned to iconic landmarks, like the pillars of creation, revealing them anew. In Webb's view, the pillars are still majestic, but they are also translucent. Their dusty veils are pulled back, and behind them and within them are countless newborn stars, their formation now laid bare. The comparison to Hubble's majestic but opaque view is a testament to how a shift in perspective from visible light to infrared can revolutionize our understanding of a familiar scene. This journey through the discoveries of Webb and the catalog of better Earths brings us face to face with a simple visual paradox. When we look at photographs taken by astronauts from the International Space Station or from the lunar surface, the sky is a profound, unbroken black. The Earth, or the Moon, is brilliantly sunlit, but the stars are absent. This seems counterintuitive. Space is full of stars. Why are they not visible in these images? The answer lies in the physics of light and photography. The sunlit surface of a planet or moon is extremely bright. To capture it without overexposing the image, cameras use very short exposure times and narrow apertures. They let in only a brief, controlled burst of light. Our eyes do the same, our pupils contracting to pinpricks in bright sunlight. The stars, while intrinsically luminous, are immensely far away. Their light, when it reaches the camera sensor or our retina in such a setting, is simply too faint to register against the overwhelming glare of the sunlit landscape. It is not that the stars are not there, it is that our sight and our technology is momentarily blinded by the proximate brilliance. To see the stars from the moon, an astronaut would have to look away from the sunlit ground into the deep black, allowing their eyes to adjust to the darkness. The cosmos is always there, a backdrop of infinity, but we must know how and where to look. This interplay of light and atmosphere defines the very color of our experience. On Earth, our blue daytime sky is a product of Rayleigh scattering, where molecules in the atmosphere preferentially scatter shorter, bluer wavelengths of sunlight in all directions. On Mars, the phenomenon is different. The Martian atmosphere is thin, but perpetually dusty. The dust particles are larger, closer in size to the wavelengths of visible light. This leads to Mie's scattering, which scatters light forward more than sideways, and is less color selective, though it tends to favor longer wavelengths when the sun is low. The result is a Martian daytime sky that often appears a hazy butterscotch or orange-brown, but at sunset, as sunlight passes through a much longer column of this dusty air, the Mies scattering effectively filters out the red and yellow light, allowing the blue wavelengths to dominate near the solar disk. So, On Mars, sunsets are blue, a world of orange days and azure dusks. Each planet writes its own poetry of light. Our solar system itself presents a series of puzzles that remind us how unique our arrangement may be. Why, for instance, does Earth not possess rings? All the gas giants have them, from Jupiter's faint dusty rings to Saturn's glorious icy system. The leading theories suggest rings are either primordial material that never coalesced into a moon, or more likely, the shattered remains of a moon that ventured too close and was torn apart by tidal forces. The rocky inner planets lack such spectacular rings, perhaps because the environment where they formed was cleaner, with less debris, or because any primordial rings they might have had were quickly accreted or scattered. Some scientists hypothesize that Earth did have a ring, briefly and catastrophically, the debris from the giant impact that formed our moon. That ring of molten rock quickly coalesced into our singular large satellite. Our moon is, in a sense, a ring that condensed into a world. Its presence stabilizes our tilt, drives our tides, and has been a companion to life's entire evolution. Perhaps in the grand trade, we exchanged a transient celestial ornament for a permanent gravitational anchor that made long-term habitability possible. Further out, mysteries deepen. The anomalous orbits of some distant icy objects suggest the gravitational tug of a large, undiscovered planet in the outer darkness, Planet 9. This hypothetical world, perhaps 10 times Earth's mass, would orbit hundreds of times farther from the Sun than we. Its detection is a formidable challenge. An even more exotic possibility, though far less likely, is that the gravitational signature is not from a planet at all, but from a primordial black hole, an artifact of the Big Bang, with the mass of a planet compressed into a space the size of a grapefruit, its gravity warping the paths of distant objects, just the same. Water, that elixir of life, is far from rare in our solar system. We find it locked in the permanently shadowed craters of Mercury and the Moon, as permafrost in the Martian soil and polar caps, and in vast quantities on the moons of the outer planets. Europa, a moon of Jupiter, harbors a global subsurface ocean beneath its icy shell, containing perhaps twice the water of all Earth's oceans. Its sister moons, Ganymede and Callisto, likely have similar interior oceans. Enceladus, a small moon of Saturn, spews geysers of water ice from a subsurface sea into space. These are not just frozen wastes, they are potential biological habitats, sealed away from the radiation of space, warmed by tidal flexing from their giant planets. The search for life is no longer confined to planets and habitable zones. It extends to these dark, subsurface abysses where chemosynthesis might fuel ecosystems akin to those at Earth's deep-sea hydrothermal vents. Even the known planets hold surprises. Neptune, the ice giant farthest from the Sun, radiates more than twice the heat it receives from our star. Its interior is a churning engine of unknown origin, powering the fastest winds in the solar system, which scream at up to 1,500 miles per hour. Its twin, Uranus, by contrast, is thermally lethargic, radiating hardly any internal heat. Why one is active and the other dormant is unknown. A reminder that similar mass and composition do not guarantee similar fate. Beyond our solar system, the cosmos exhibits even more extreme phenomena. Astronomers using the Hubble Space Telescope discovered a supermassive black hole weighing over 1 billion solar masses that has been ejected from the core of its galaxy and is now hurtling through intergalactic space at 5 million miles per hour. This incredible event was likely caused by the merger of two galaxies and their central black holes, with the resulting gravitational wave kick propelling the behemoth on a lonely, eternal journey. It is a demonstration of the universe's raw, gravitational violence on a scale we can barely comprehend. Our own star, the Sun, while life-giving, also harbors a latent threat. Solar storms, eruptions of magnetized plasma called coronal mass ejections, can wreak havoc on a technological civilization. In July 2012, a storm of a magnitude not seen since the Carrington event of 1859 missed Earth by a week. Had it struck, it would have induced catastrophic currents in power grids, frying transformers and causing blackouts that could last for months or years, collapsing modern infrastructure. A surprise storm in June 2022 did strike, creating brilliant auroras seen as far south as Calgary, a beautiful but potent reminder of our vulnerability to our star's temper. In the stellar graveyards, we find other strange tales, vampire stars, in close binary systems, where a smaller, denser star, like a white dwarf, siphons hydrogen fuel from its larger companion. The stolen fuel rejuvenates the vampire, making it hotter and bluer, masking its true age, while eventually leaving its donor star depleted and dying. It is a celestial parasitism, a dance of stellar life and death. If we could average the light from all the stars, galaxies, and nebulae in the observable universe, what color would it be? After meticulous analysis of vast sky surveys, astronomers found the answer: a warm, creamy beige, officially dubbed cosmic light. It is a blend of the reds of old stars, the blues of star-forming regions, and the light from countless others, a testament to the average stellar population of our cosmic epoch. Our sense of scale is constantly being recalibrated. Jupiter, the king of our solar system, could swallow 1,300 Earths. Yet we now know of exoplanets that dwarf even Jupiter. The gas giant AB Aurigae b, a planet still in the throes of formation around a star, only 2 million years old, has a mass of about 9 Jupiters. It orbits its star at a distance nearly twice that of Pluto from our Sun. Its formation appears to be occurring through a process called disk instability, where a massive clump of gas in the protoplanetary disk collapses directly under its own gravity, rather than the slower core accretion model that built our own solar system. This diversity of formation mechanisms suggests an even greater diversity of planetary systems than we imagine. But is that the upper limit? The object, GQ Lupi b, orbiting a young star, has a radius 3.5 times that of Jupiter. It blurs the line between planet and brown dwarf, a reminder that nature does not always respect our tidy categories, and stars themselves can reach sizes that defy comprehension. The hypergiant UY Scuti has a radius over 1,700 times that of our Sun. If placed at the center of our solar system, its photosphere would engulf the orbit of Jupiter. We are but motes in a cathedral of incomprehensible scale. At the opposite end of the scale density spectrum lie black holes, where gravity achieves its ultimate victory. Supermassive black holes, like Ton 68, with masses of 66 billion suns, anchor the centers of galaxies. Their origins remain a mystery. Did they grow from smaller seed black holes, or did they form directly from colossal clouds of gas in the early universe? They are the engines of quasars, the sculptors of galactic structure, and perhaps the ultimate destiny of vast amounts of matter. Space is vast, but it is not uniformly filled. We find great voids, regions hundreds of millions of light years across that are unnervingly empty of galaxies. The Eridanus supervoid is one of the largest known structures in the universe, a spherical emptiness 1.8 billion light-years wide. Its existence challenges our understanding of how matter clustered after the Big Bang. Within our galaxy, nebulae like the tarantula serve as stellar factories, while others are the glowing shrouds of dead stars. The Cat's Eye Nebula, a complex structure of ejected gas from a dying star, resembles a cosmic butterfly or an hourglass, its intricate shapes governed by magnetic fields and binary star interaction. Our own solar system continues to deliver surprises. The dwarf planet Haumea, a rapidly spinning egg-shaped object in the Kuiper Belt, completes a rotation in just 4 hours and possesses a faint ring system, phenomenon thought to be the sole province of the giant planets. Its ring is likely the debris from an ancient collision, a frozen record of violence. The star Fomalhaut, surrounded by a vast, sharp-edged disk of debris that looks like the Eye of Sauron, shows us a planetary system in a different stage of evolution, where planets are shepherding dust into rings and gaps. And then there are the visitors. In 2021, the largest comet ever observed, C-2014, UN 271 Bernardelli-Bernstein, entered the outer solar system. Its nucleus is about 85 miles across, larger than many dwarf planets. It will make its closest approach to the Sun in 2031, but will remain safely beyond Saturn's orbit. Its arrival from the distant Oort cloud tells us that the outer solar system still holds unknown giants at the most extreme densities imaginable, inside the corpses of massive stars that have become neutron stars. Matter is compressed to such a degree that atomic nuclei are squeezed together into exotic forms, long strands and sheets dubbed nuclear pasta. This material is phenomenally strong, perhaps 10 billion times stronger than steel, a testament to the unbelievable forces at work in nature's most compact objects. Pulsars, rapidly spinning neutroners, act as cosmic lighthouses. Some, like the Black Widow pulsar, are in the process of evaporating their body companion with their fierce radiation, a stellar-scale version of the vampire phenomenon. All these discoveries, from the potentially life-bearing super-Earths to the cosmic oddities, flow from our insatiable need to understand our context. They tell a story of a universe that is not just vast, but fantastically creative, capable of environments and phenomena that stretch the limits of physics and imagination. The James Webb Space Telescope, in its silent orbit, is our current vanguard in this exploration. Its mission, to see the first light, to sniff the atmospheres of other worlds, to map the architecture of creation, is the next logical step in a journey that began when the first human looked up at the night sky and wondered, but what of our place in this? The discovery of better Earths invites a speculative and perhaps humbling thought experiment. If we could choose a world not by proximity, but by optimal conditions for a long-lasting advanced civilization, what would it look like? A super-Earth 2 to 3 times our planet's mass, orbiting a calm, long-lived orange dwarf in the galactic habitable zone, with a stable axial tilt, a robust magnetic field, and a climate slightly warmer than ours, with continents and oceans in a balanced distribution. It would be a world with more real estate, a thicker protective atmosphere, and a sun that promises tens of billions of years of stable light. Such worlds, we now know, likely exist. This brings us to the ultimate pragmatic question. Colonization. Is our destiny to remain on this Earth, or to become a multiplanetary species? Mars has long been the focal point of this dream. It is close, it has resources, a day length similar to ours, and evidence of past water. But it is a harsh, frozen, radiation-bathed desert with a thin, unbreathable atmosphere. The endeavor would be a monumental test of human resilience and technology. Yet, it may be a necessary step, not just for exploration, but as a hedge against planetary catastrophe. But other, more exotic candidates exist. Consider Ceres, the largest object in the asteroid belt. This dwarf planet, about the size of Texas, is a water-rich world. Its surface is a mixture of rock and water ice, and it may even harbor a deep, briny subsurface ocean. For future spacefarers, Ceres could be a crucial way station. Its low gravity, just 3% of Earth's, makes landing and launching easy. It could serve as a refueling depot and mining center, processing the water ice into hydrogen and oxygen for rocket fuel. It could be the gateway to the outer solar system, a hub for exploiting the mineral wealth of the asteroid belt. Living there would present immense challenges, countering muscle and bone loss in microgravity, shielding from radiation, creating closed-loop life support systems. But as a strategic outpost, a piece of cosmic infrastructure, its value could be immense. These visions of colonization force us to think in terms of resources and logistics on a solar system scale. They also force us to reflect on the unique balance of our own planet. We spoke of worlds with different land-to-water ratios. What if Earth itself had a different balance? If it were almost all water, a global ocean hundreds of kilometers deep, it would be a world of perpetual fog and crushing pressures, with life, if it existed at all, confined to strange, isolated pockets. If it were 50-50 land and water, with sea levels 2 miles lower, the continents would merge into a single vast supercontinent. The oceans would shrink into isolated basins, and the climate would become extreme, with brutal deserts and catastrophic droughts as the hydrological cycle faltered. Our current configuration, the blue marble, with its shimmering interconnected oceans and separated continents, appears to be a delicate, fortunate equilibrium. It drives the climate, nurtures biodiversity, and has allowed our species to flourish. It is a balance we are only now beginning to appreciate, and one we are carelessly testing. The search for life and homes among the stars is therefore a journey outward that turns our gaze back inward. Each new exoplanet discovered holds up a mirror to Earth, showing us what is universal and what is singular. Each strange phenomenon, uncovered by Webb, deepens our understanding of the physical laws that govern everything, including the biology on our own world. The cosmic latte sky, the sandstorms of brown dwarfs, the eternal red sunsets of Kepler 18.6f, the potential oceans of Europa. These are not just curiosity, they are chapters in a single grand story, the story of a universe of matter becoming complex, and in at least one known precious instance, becoming conscious of itself. We stand at a remarkable juncture. For the first time in history, we have the tools to move from speculation to evidence in the search for other living worlds. The James Webb Space Telescope is more than a machine. It is a question posed to the cosmos. Are we alone? The 24 better Earths are not answers, but they are promising addresses where an answer might one day be found. The distances remain forbidding, the challenges of interstellar travel perhaps insurmountable for millennia. But to know that such places exist, that the universe may be teeming not just with life, but with worlds that are kinder, gentler, and more enduring than our own, is a source of profound hope and perspective. It tells us that Earth, for all its wonders, is not a prison, but a cradle, a beautiful, fragile, and perhaps somewhat rudimentary cradle. Our responsibility is to safeguard it, to nurture the life it bears, even as we dream of the stars. For in learning to live sustainably on this world, we learn the first principles of surviving on any world. And in learning to read the light from distant suns, we begin a conversation with the cosmos that may, in time, show us that life and intelligence and perhaps even wonder are not accidents, but cosmic imperatives. The night sky is no longer a ceiling, it is an ocean, and we have just begun to dip our toes in the water, feeling the pull of its infinite tides. The journey has just begun. May we have the wisdom to cherish our point of origin and the courage to navigate the vast, starry deep that calls